part of one or scene one, you know what I'm talking about?
Yeah.
So the people in the crowd in the stadium, that is the medium, and the particles, they move up and down, right? As the wave sweeps around the stadium. So you're transferring energy from one side of the stadium to another, but you're not transferring any matter. And that's like a key idea. Sound is a longitudinal wave. The particles, for instance, if a sound is going from me to those cabinets over there, the air molecules are going like this. They're oscillating back and forth along the direction of motion. Longitudinal, along. Transverse means perpendicular. Okay, I'm not going to do that. Hang on. I want to get, there we go, that's what I want. So a tuning fork, you're going to be using tuning forks today for the lab. And a tuning fork generates a sound wave, a longitudinal wave, by, okay, pretend I'm a tuning fork and my arms are the tines of the tuning fork. So the tuning fork does this, and what that does is, when it's apart, it's compressing the molecules together, and then when it goes back toward the center, it causes what we call a rarefaction. So it sort of leaves like a partial vacuum there. So it oscillates the air molecules back and forth as it goes along. Okay, now, there's something called a standing wave, and actually we won't talk about that till next Tuesday in lecture. But if you've played a musical instrument, or even if you've watched someone play a guitar, or a violin, or a cello, or a piano, those are setting up standing waves on a string. And if you've ever looked at a guitar or any stringed instrument, you know that the different strings usually have different thicknesses, and that's that's because the resonance, the standing wave that you can set up in the string, depends on its density, and it also depends on its tension, how tight you have it. So that's why you can tune a guitar or violin, whatever, by turning the little key at the end of the string. So how many of you know what I'm talking about there? Okay, you have some sense of this. Good. Also, wind instruments work by setting up standing waves in a column of air, and that's what you're going to do today. You know, if you've watched a trombone, they vary the length of the tube of the trombone by pulling that U-shaped piece out, don't they? And that makes the air column longer, and if you push it in, it makes it a shorter air column. It turns out the sound that causes a resonance depends on the length of the air column. So also pipe organs, have you ever seen a pipe organ? Mm-hmm. Those work by setting up a resonance in a column of air. Flutes and other instruments where you, trumpets, where you push keys in or where you cover up holes. In those, you're not changing the length of the air column, but you're changing where it can make a node or an antinode. And I don't think I've got a standing wave on this, but I have a transparency. You don't see me using the transparency. Roll this into position real fast here. I'm going to show you what it is you're going to be doing. So,
Oh, no, you're fine.
Side foot.
You're fine.
Okay, so when you set up these resonances in the air column, it turns out this represents a half a wavelength, and then this little part is a fourth of a wavelength. And the part where it's like the thick part of the ellipse, that's an antinode, it's called. It's a region of maximum interference. And then here, the ends of the ellipses, that's called a node. It's actually a place where the sound waves cancel out. And we'll talk more about this in class. But what we're going to do is start by finding L1, where we get the first, you're going to get a loud sound there when you're at that distance. Then we're going to lower the water level and find L2. Lower it again and find L3. And really, I guess that's all you need to worry about there. There was an error in this. I just want to be sure I fixed it. I'm not sure I remembered to edit it. I did. Okay. So let me show you what's going on. All the rest of this is just going to be on the blackboard. Okay, so you're going to use 2 tuning forks. You're going to use an apparatus like this, and these are pretty old, and some of them may leak down at the bottom. So you're just going to have to do your best. And I'm going to ask you to, at the end of the lab, try to transport this to the sink, and then you'll need to secure this because it'll fall out of the base sometimes. Holding the pole and the tube, maybe you and your partner can empty it into the sink. Okay, you just want to upend it into the sink. Okay, so to start with, I'm going to say you can pour into the can, and it's going to try to reach a level, well, it is going to reach a level where both levels are the same. So that's how you're going to control the height of the water in here. And here's the thing, you want to, you may have to end up taking some water out in order to get to the lowest level. And I'm going to have to add a little more to get to the highest one. Not that much more. So can you see the water in the tube at all from where you are?
Yeah.
I may have to add more yet. We'll see. Okay, so let me see if I can show you what I'm talking about. By the way, a couple of points about tuning forks. Please do not hit them on a hard surface like the floor or the table.